So Properties Matter PowerPoint, I'm going to go through this information with you right now. You can highlight all of this information within your notes. Matter is anything that has mass and takes up space. We've talked about that for the last few weeks. We've also defined mass and volume, but here's the official definition for you. Mass is a measure of the amount of stuff an object contains. That stuff we've classified as atoms or molecules. And I don't want you to confuse mass with weight. Weight is a measurement of gravitational attraction of objects to one another. We measure our gravitational attraction to Earth, which is the largest object we're associated with. We'll talk more about that when we get into physics. And volume is a measurement of the space occupied by an object. Now, when we try to classify matter, we can put it into two major categories. One is extensive and the other one is intensive. Extensive matter depends on the amount of matter in the sample. Mass, volume, and calories are a few examples of that. But if you take mass as one of those examples, and you use an object like a Twinkie, if you have one Twinkie, it's going to have a certain amount of mass associated with it. If you had two Twinkies, that mass increases twofold. So it does depend on the amount of matter associated with that mass, just like volumes and calories would be the same way. Intensive properties, however, depend on the type of matter, not the amount present. Hardness, density, and boiling point are a few examples. Again, boiling point, if I use water as an example, water will boil at approximately 100 degrees Celsius at sea level, and it doesn't matter if you've got 400 milliliters of that or if you've got 4 gallons of that water. The boiling point is the same. So it's just the type of material, it's not the amount. Whereas alcohol, rubbing alcohol might boil at a different temperature. We can classify classify matter in a couple different ways. Also, we've got physical properties. Physical properties are ones that are observed and measured without changing the material's composition. For example, color, hardness, melting point, and boiling point fit into those categories. Color doesn't change the material's composition. We can talk about a white piece of paper, or we can talk about a pink piece of paper. It doesn't change the fact that it's paper. Same thing with melting point. You can take an ice cube, melt it down into liquid water, and it doesn't change the fact that it's still water. Whereas chemical properties are observed by changing the composition of the material. The ability of something to burn, decompose, ferment, or react with are a few examples of that. In the gas lab, we identified Alka-Seltzer in combination with water will produce carbon dioxide gas. That's a chemical property. It's something that's changing in form. States of matter we've identified in 3 different categories: solids, liquids, and gases. Solids don't flow. They have a definite shape, definite volume, whereas liquids have a definite volume, but it takes the shape of a container. It does have the ability to flow. Gases are somewhat similar. They have a definite volume or shape. I'm sorry, they do not have a definite volume or shape, and they can also flow. Vapor is just a term that's associated normally when you've got a liquid or solid at room temperature, and you change that temperature. Maybe you raise the temperature of water past 100 degrees Celsius and change it into a gas form. That gas would be known as water vapor. So again, it's when the gas is normally a liquid or a solid at room temperature, and then you change its phase into a gas. It's known as a vapor. This chart here identifies solids, liquids, and gases, and identifies whether they have definite volume or not. Solids do have a definite volume, just like liquids have a definite volume, but gases take the shape of their container. They fill up whatever space has been given, so the volume can shift and change around actually depending on where that's located. Definite shape, solids definitely have a definite shape. Liquids don't, because they take the shape of their container just like gases would take the shape of their container. Result of a temperature increase. Well, solids, if you increase the temperature of them, they have a small expansion, just like liquids have a small expansion, whereas gases will expand quite a bit. And then, will they compress? Solids are difficult to compress. Liquids are also difficult to compress, but you can take gases and compress them down into smaller spaces and pressurize those things like you would in, for example, a helium balloon container. The fourth state of matter, which we aren't going to discuss too much in here, is plasma. It's a highly ionized form of matter, typically found in the sun as an example. Three phases of matter. Again, we've been talking about that. We can take a look at them here. In the left beaker, we've got solid. In the middle beaker, we have a liquid. And in the beaker on the right, we have a gas. Notice that there's a top on that part. And when you change from one thing to another, for example, when you change from a solid over into a liquid, that process is called something. We call that melting. When you change from a liquid over into a gas, that process is evaporation. And you can reverse the process and go on the opposite direction. You go from a gas back into a liquid, that process is condensation. And when you go from a liquid and change it back into a solid, that process is freezing. This is simply showing you copper in a solid form where molecules will vibrate back and forth. Notice that the temperature is pretty high here. Anything less than that it would be in solid form. But you increase the temperature significantly, and it is possible to take copper, melt it down into a liquid, and once it gets past 2,594 degrees Celsius, you can change it into a gas phase. Notice that the molecules move faster and they're more spread out. Physical changes and chemical changes. Well, physical change will change the appearance of the object without changing the composition of the material. Boiling, melting, cutting, bending, splitting, and cracking are some examples of that. You can bend a piece of paper, it's still paper. You can melt an ice cube, which is solid water, into liquid water. It's still water. Can it be reversible or irreversible? Well, in this case, it kind of can be either. You can reverse the melting process by freezing the item again. Sometimes it's irreversible. You can't untear a piece of paper. Chemical changes are changes where a new form of matter is going to be formed. So rusting, burning, decomposing, and fermenting, you're going to get something that's completely different. You burn a piece of paper, you're not going to get the paper back. In that case, it's not really reversible. It's going to be pretty tough to do that kind of a thing. Again, chemical changes are changes where one or more substances are converted into different substances. Oftentimes heat and light are evidence of that kind of chemical change or reaction. And we got properties of compounds. The chemical changes, when we talk about changing compounds such as table sugar into its individual components, carbon, hydrogen, and oxygen are elements that make up table sugar. Sodium chloride, sodium, and chlorine make those things up, and water is composed of hydrogen and oxygen. These things have different properties. Sodium, for example, is an explosive metal, whereas chlorine is a kind of a poisonous gas, but together they're going to make table salt, sodium chloride. So those properties can be different depending on what you do with those particular substances. As we said before, chemical changes will change substances from one thing to another. Iron plus oxygen forms rust, which is a chemical property of iron. And during chemical changes, the composition of matter always changes. Chemical reactions are when you've got more substances that are changed into new substances. So we talk about the beginning parts of those products as being reactants. That's the stuff that you start with in a chemical reaction. And what you get out of it is a set of products. It's like taking a set of ingredients, brownie mix, an egg, and some oil, stir it all together, and you get yourself a brownie mix, put it in the oven, and you get brownies. Well, the reactants are all the ingredients, and the product is the actual brownie that you get. products are going to have new properties. A brownie is way different than the egg that made it, the oil that was combined in there, as well as the brownie mix itself. When you put this stuff together into a chemical formula, the arrows that are produced are going to point from the reactants to the new products. We'll talk more about that when we get into chemistry. When you recognize chemical changes, what you look for is a few different things. Energy can be absorbed or released, which means temperature changes are going to happen. It could be hotter or colder, it's possible. Color changes can take place. Gas production, bubbling, fizzing, or any kind of odor change or smoke is generally a good indication you got chemical changes. Formation of precipitates, that's a solid that actually kind of forms as it comes out of a solution. It's not dissolvable. And irreversibility. It's not easily reversed, but there are examples of these that are not chemical. Boiling water bubbles. That's not a chemical reaction. But again, taking something like a piece of paper and burning it is pretty irreversible. You're not going to be able to get that back. And the last little bit of information deals with law of conservation of mass, and it's associated with Lavoisier, Antoine Lavoisier in 1789, identified that any chemical reactions that take place, the mass of the products is always going to be equal to the mass of the reactants. But before his time, people really didn't know what happened and why burning wood or paper would appear to have less mass in ash form. People were curious about where did that mass go? What happened to the matter? Well, that experimentation that he did identified his ability to collect all of the gases that were produced from the combustion process and retain it and be able to mass it before and afterwards and come up with the masses being the same. Here's a figure identifying two vials. The first diagram, letter A here, identifies two vials with two clear chemicals having a mass of 43.43 grams, and two vials over here on the right side in figure B identifying that they've been combined together and the masses are the same. Well, the reactants are what you start with, the products are what you end up with, and the original mass was 43.43 grams. The final mass is 43.43 grams. So that chemical reaction is identifying the fact that conservation of mass is indeed taking place. And a pretty important piece to take with you as you move through labs in this class.